では、第54回の ASE セミナーを始めたいと思います。はい、私、東京大学情報基盤センターの下川でと申します。So, we are now start the 54th ASE seminar. And this seminar is the advanced supercomputing environment, and so we are invited the foreign researchers. So in this seminar, in this seminar, so we are the topic is the Kokkos and the performance portability. So we have the 3 talks in this seminar, and two of them are given by the invited speaker. So the Dr. Julian Vigo, no, sorry, and the Yuichi Asahi, Dr. Yuichi Asahi, from the CEA, and Maison de la Simulation,
which means House of Simulation in French.
Okay, the Maison de la Simulation, the CEA. Okay, so let's start with the first talk, and the first talk is the speaker is Dr. Julian Vigo, the CES. The title is the Kokkos and HPSF, the reason of choice at the CES. So the Dr. Vigo is he's the team leader of the science of the computing team of the CES. And so please join me in the welcoming to Dr. Vigo. So please start your talk.
Thank you very much. So I just lost connection, but I think it's reconnecting, so we should be good. Okay. Yeah, here I am. Share screen.
Yes, please share screen.
So yeah, I will talk today about Kokkos, about the High Performance Software Foundation, HPSF, and the CEXA project at CEA, and the reason we made the choice to go with this library for GPU and performance portability. But before telling you that, let me give a bit of context. Okay. The screen sharing doesn't seem to work very well. So 2 years ago, the CEA, which is the French Atomic Energy Commission, started to look at the option for GPU. The reason for that is that CEA is a large institute with about 20,000 researchers all over France, organized in 4 independent divisions, where HPC is a tool that we use at every level. CEA is one of the operators of the European Supercomputer Center, and we are now entering the exa-scale era, and we all know that exa-scale means GPU. If you look at the ratio of the performance of the top 500 provided by GPU accelerated computers, in 20 years, we went from 0 to more than 3/4. And in fact, this doesn't include the last top 500 ranking, where we are now at more than 80% of the computing power provided by GPU accelerated computers. In Europe, we will have 2 exa-scale machines, one in Germany that will be Grace Hopper based, and one in France at CEA that we will operate. And the technology for this one is not selected yet. It will come next year, that's the plan. And this year, we still don't know what the actual vendor will be. Will it be Intel, AMD, NVIDIA? We don't know. So that means we need to redevelop our existing CPU application with GPU in mind and with performance portability as the main goal. And for that, we need programming models, we need middleware that act as a catalyst to leverage the raw performance of the hardware. 2 years ago, application developer, they saw a lot of options, where to go, different option of programming model for GPU, and there was not one option that was better than the other, so a lot of them were just waiting for the good option to appear, or at least to be sure that they are not alone in making a choice. And in France, in Europe, we had this need to have something that we can rely on, something that is well suited to the specific needs of our applications, well suited to the specific hardware we operate. That's not always the same as the hardware that is available in the US, for example. And that is something where we can trust in the long term that the roadmap will still be adapted to the specificities of our hardware and applications. And that was the reason to launch this exa project. The goal of the project is first to provide such a sustainable middleware to act as a catalyst for the application to leverage the hardware. The second aspect was to take some application and adapt them to GPU, a demonstrator to prove that the solution that we have selected works. And the third goal is to do some dissemination, to provide trainings, and to embark as many applications in the choice. But what to use exactly? When we look at GPU programming, there are many available approaches. Some are more low level, some are more high level. You can go from approaches that offer raw performance by basically writing something that looks like assembly. Then you have some things that looks more like imperative languages and that offer a little performance portability on top of that. And then you have solutions where you also add domain abstractions or even libraries that you call from the CPU and that make the GPU use completely transparent. In our case, what we wanted is something where we can write GPU code, not something where we just assemble pre-existing GPU, pre-written GPU codes. And the second point is that we wanted a level of abstraction that offers performance portability, but that is as general as possible, that we can use in as many applications as possible. So we went for this general purpose imperative GPU programming language. And in this category, there are still many options. CUDA, HIP, Kokkos, ASE, and so on and so on. Our choice, the first criterion, was to go with something that is production grade, a tool with public support. If we look, for example, at some things like Raja, this is a very nice library, but the contact we had, the developers were more interested in their local community than make it a widely used tool. When we look at adaptive CPP, adaptive C++, and implementation of the exa-scale standard, it's more of an experiment of a university than a tool that aims to be a production tool right now, or at least when we looked at it 2 years ago, that was the case. The second criterion was to have something that is vendor neutral. We don't want a tool where a single vendor has a big interest in the library. So for example, if we look at CUDA, HIP, these are really linked to one specific vendor. OpenACC also. And the DPC++ or WAN-API implementation of SQL is also something that is very closely related to one vendor. Even if it can run on different backends, you still are closely linked to the choices of one vendor. So in the end, for our choice, for this criterion, we had two main options available. On the one hand, Kokkos, on the other hand, OpenMP target. And when you look at these two programming models, they have different syntax, but for something like a parallel loop, you express basically the same concept in two different ways. So you express that you execute a loop in parallel where one thread on for each iteration. Each iteration executes the same workload, but identified by a different unique identifier, and you execute that nj times between 0 and nj minus 1. As you can see, I've tried to use color to show that we see the same things in the two programming models. The syntax is different, but the concepts are the same. This is the same for the memory transfer part. You have different syntax for these two languages, but in the end, the concepts are very similar. There are some small differences. For example, on the Kokkos side, you see that you expressly put in the type the information about where a given array resides. One in OpenMP, this is implicit. You have to keep that in mind, or you can use comments, but this is not part of the things that are checked by the compiler and that you express in the program. Kokkos also offers multidimensional arrays, while OpenMP, well, this relies on what is available in the language. But these are minor differences. Basically, the two options are very similar from a programming model point of view. And in terms of compilation, that's where you start to see the main difference. Kokkos is a C++ template library. It doesn't specifically, it doesn't generate specific code. It relies on vendor-provided C++-like backends. So you have multiple backends, for example, OpenMP, CUDA, WAN-API, HIP, and you select which one to use at compile time. At compile time, you choose to compile for OpenMP, for example. And you can choose 3 different backends at the same time in one compilation. One will be your device parallel backend. One can be your host parallel backend, so you can have parallelism on the GPU, parallelism on the CPU, and you always have the option to add the serial backend. On the OpenMP side, OpenMP is an annotation-based, so it has to be supported by the compiler and compatible with the target construct. If you have a OpenMP without target support, it doesn't work, and compatible with the specific hardware you want to target. So that means that each vendor has to provide its own OpenMP compiler, where usually it's based on a common basis of LLVM infrastructure, but there are also the base compiler like LLVM and Clang and GCC on the other hand that try to support that. So to come back to our initial choice, basically we have a choice between 2 approaches. OpenMP is an annotation-based approach that works very well with imperative languages like C, like Fortran. while Kokkos is a library approach that works with a language that supports encapsulation, and Kokkos it's for C++. With Kokkos, you need to rewrite your application. If you have a Fortran application, you need to rewrite it to be then Kokkos-based. But with OpenMP annotation, you still need to redesign your application. Maybe you can keep a part of the code, but if you want it to work and to work efficiently on GPU, you have to redesign a lot of things. And in the end, the annotation is based on compiler support. It has the potential for many optimization. You are inside the compiler when you implement it, so you can do whatever you want with the code. While Kokkos is based on the choice between various backends. So it's just a template library that will select one backend at compile time. It can do less crazy things, but it's also simpler to implement. And in our experience, when we have a new machine with a new hardware, this is faster to work. The Kokkos way is simpler to implement and faster to work than the annotation-based way where you need to work inside the GPU. So, okay, did I lose the connection again? Yep, it looks like. Okay, so while it tries to reconnect, let me say that I have shown that in Kokkos and in OpenMP, you have support for parallel loops, you have support for memory transfer, but these are not the only things that will be available in Kokkos. As a matter of fact, you also have other parallel patterns. Yes, the for, but also reduction, scan. You have nice things like support for naming your loops, which makes it easier to debug, to trace, to evaluate the performance. You can get a trace with the time, with name that makes sense for you in the trace. You have a choice of various policies that you can add to your parallel loops that make it possible to have not only 1D iteration, but also multidimensional iteration. You can also add hints like chunk size, like tiling, to make the performance portability real, and not only portability. You want to give these hints for performance. You can explicitly select your execution space in the loop policy to choose where your loop will execute. You can have one loop execute in parallel on the GPU, and then one loop in parallel on the CPU. And depending on the backend you choose, you can change that. If you want to compile for CPU only, the loops that you prepared for GPU will run on the CPU instead. You have support for hierarchical parallelism. As you know, GPU are hierarchical. You have multiple levels of parallelism in a GPU, and you have construct to support that in Kokkos. You have support for asynchronicity. Sending some workload to the GPU is something that is asynchronous, and you find that in Kokkos, you can execute different parallel loops together. They are not synchronized by default if you use a different execution space. Kokkos also brings support for views that are basically multidimensional arrays. They behave like a C++ shared pointer. That means that you don't have to manually manage memory allocation. Kokkos will allocate, and as long as you have one view that access this memory, the memory will remain allocated, and as soon as you don't need it, it will be automatically deallocated. You also have the naming here, like for loops. You have support for the various kind of copies and transfer between CPU, GPU, etc. You have support for things that are a bit smarter. For example, this mirror view that make it possible to have a view from the CPU on data on the GPU that will be updated only when you need to update it. The views also have what is called in Kokkos a layout. Basically, you can have a layout left that is similar to the Fortran layout and a layout right that is similar to the C or C++ layout. And the advantage of that is that you can switch from one to the other. And in fact, if you want the best performance, you want to switch depending on whether you're on CPU or on GPU. That way, the memory access will be the most efficient. So this is just a quick peek at what's in Kokkos. But in fact, this is just part of the features of Kokkos. And if you look, Kokkos has much more than that. Some features for performance portability, some features for working around the quirk of each backend, some features for quality of life. And you need all of that if you want to actually support portability between vendors. So yeah, redeveloping all of that in our point of view was a lot of work. So that's part of the reason to choose an existing library. But in fact, when you look at a Kokkos-based application, you have the application that uses the Kokkos library, and the Kokkos library offers portability for various backends. But that's not all you will use. You will also use other libraries like Kokkos kernel that offer support for linear algebra on top of Kokkos, as well as other small libraries that are designed in the ecosystem of Kokkos, like Kokkos FFT. You will have a talk just after about that will mention this point. In addition, you have tooling, because a library without the associated tools for debugging, for profiling, for tuning, etc., is basically very limited. And in the Kokkos ecosystem, you also have a whole lot of support, documentation, online documentation, tutorials, trainings, hackathon. If you go to the Kokkos, you have these really good videos on YouTube to train and to learn how to use it. You have in France nowadays we have multiple trainings every year to learn how to use Kokkos, etc. This is also something that is really important to make the library usable. And in the ecosystem, on top of the Kokkos project, you have quite a lot of libraries like Trilinos, like PETC, that nowadays use Kokkos and are compatible with Kokkos. Okay, so this is from a technical point of view, and the reason this works and this ecosystem is so well furnished is because Kokkos is not new. This is something that started more than 20 years ago. It was part of an internal project at DOE in the US, and then it evolved and to be extracted from the project. And then with new hardware becoming available, it evolved over the years to become what it is today. And what it is today is not only a very good library from the technical point of view, but this is also a library that is used as a stepping stone for the standard C++ standard. So the standard C++ ISO is moving to add new features that are useful for high-performance computing, such as parallel algorithms, sender receivers, etc. And the Kokkos team was part of the effort and led some of the effort to include features in the C++ standard that are extremely useful for us. For example, multi-dimensional array in C++ and this span, they come from the Kokkos team, from the experience of Kokkos, and the Kokkos team worked for the standardization of that. Vectorization with stdcmd. Linear algebra, nowadays in C++ you have support for linear algebra in the C++ standard, also something that was pushed by the Kokkos team. And there are much more like mixed precision, etc. That was pushed by the team. So the ISO C++ standard will will include all of that, which is nice. But Kokkos is still interesting in this case because it offers something that is available earlier. To get into the ISO C++ standard, you need to make a consensus with the C++ community, including users from very different domains. So it takes a lot of time. And Kokkos offers you right now the features that will be available later in the C++, and it offers that with a stable API that will move to offer compatibility with this standardized C++ once it is standardized. In addition to that, the Kokkos implementation takes into account GPU compatibility. That is not always the case for the GPU, for the standard C++. And while I'm reconnecting, let me talk about a second point. So the standardization effort was a very important point for us. But in addition to that, the Kokkos team worked in the creation of something that is called the High Performance Software Foundation. And the High Performance Software Foundation is intended to be a place, a neutral hub for open source projects targeting high performance computing, where the projects can be developed independently of any institution, can be developed together, and can share the development effort. And this is something that is proposed by the High Performance, by the Linux Foundation. So the High Performance Software Foundation is made of a governing board funded and where the various High Performance Software Foundation members have a vote. And on the other side, there are projects like Kokkos. Kokkos is now a High Performance Software Foundation project that take part in the technical advisory council of the foundation. The governing board will fund some aspects of the development of this project, not the development itself. Each project is still developed by various developers all over the world, but things like CI, like testing, things like outreach, things like developer meetings, all of that can be funded by the High Performance Software Foundation. So, as I said, Kokkos is now a High Performance Software Foundation project. It's not anymore a DOE project. So the High Performance Software Foundation is the place where the project is now developed. And so, as I said, there are two ways to join the foundation. One is as a member, where you will participate in the foundation and fund the foundation because you think this is an important thing to do. And the other is as a software project because you are interested in becoming a project shared beyond a single institution. Regarding the software that are currently part of the foundation, we currently have reshare project like SPAC, Warpex, Amrex, E4S, Aptainer, Kokkos, Charlie Cloud, Trilinos, Viscores, or HPC Toolkit. All of those are now HPSF project. And for all these reasons, the CEA and the SEXA project inside CEA made the choice to go for Kokkos. So the strategy we chose was what we called adopt and adapt. So basically, we choose Kokkos because it is a very strong technical project. We like the software architecture. We think it's a major free project that works well, but also because of this aspect, the project is now owned by this independent foundation, the High Performance Software Foundation, and the project is really a place for the standardization effort in the ISO C++ standard. So it's a stepping stone for the future of HPC. So this is why we chose to adapt Kokkos, but still it needs some adaptation. Adaptation for the European hardware, adaptation for the European applications. And that's the reason we funded the SEXA project at CEA to not only use Kokkos, but to take part in the development of Kokkos with a team plan of 13 researchers from all over CEA. So I said that CEA is made of independent division. This is a project that joins all of CEA. We have recruitment. 3 of them are done to work on Kokkos. We are still looking for 5 more people. And this is a team that is growing with 3 more recruitment expected for next year. In addition to this core team that works on the development of Kokkos itself, we have an extended team where the application demonstrators are developed. And this extended team is not funded by the project, but they work with us because they think that they are interested in using Kokkos. And beyond that, of course, we have the community, the expert network that give us feedback on what are the needs, the requirements. And this is where we do most of our work of dissemination of training. In terms of what we have done, we have worked on various things: documentation, training, support for our application. We have worked on improving the quality of the software. We've worked on the CI, especially worked on the SPAC recipes. We target as a very important target the code migration, so code that want to go to Kokkos from Fortran, from C, from OpenMP, CPU, and that we try to provide them with an easy way to migrate to Kokkos. We've worked on specific hardware that we have available and that we want to make efficient with Kokkos, and we have worked on the development of specific libraries like DDC, Kokkos FFT, or Kokkos COM to improve support for some specific requirements. So you will have a bit more information about Kokkos FFT in the following talk. And with that, let me conclude. So first, sorry for the technical difficulties. It seems like the connection I have doesn't work very well. But in our case, we were really happy to use Kokkos as a strong vendor-neutral, performance-portable programming model with support for GPU. With CEXA and HPSF, we ensure that the solution works for the application we have, and we have sustainability in mind. This is not only for the next few years. We invest in the long term, and thanks to that, there is a strong dynamic that works at the CA, but also beyond in France, in Europe. With new application, new synergies, new collaboration that appear every weeks, because the people that were wondering which way to go to GPU, they now have a solution, they now have a common solution, they can work together, share this, and this is something that works quite well, and we are really happy about. And with that, let me thank you all for attending, and if you have any question, I would be very happy to answer them. Okay.
Okay, so that's time to go to the next one. So thanks to speaker again. Okay, so the next speaker is also the invite speaker, the Dr. Yuichi Asahi, from the CES. The title is the development of the performance portable numerical libraries for exa-scale plasma turbulence simulation. So please join me in welcoming the Dr. Asahi.
Can you listen to me?
Yes, I can hear it.
So following Julian's talk, I'll talk about the development of performance portable numerical libraries for the exa-scale plasma turbulence simulation. And this work is done in a collaboration with the other CE department and for the École Polytechnique from Switzerland and under CEXA project. So this is their motivation, and the numerical fusion simulations are very costly, and it's even bigger because the targeting devices are also getting bigger. So the bigger devices are bigger simulations. So we need their best simulation capability using the best simulation, best supercomputers. Until quite recently, we have great time with this Zeta code written in Fortran with OpenMP. We have happy days because in all we have to do is just using the MPI plus OpenMP code for CPUs. Because supercomputers are getting better and better, all we have to do is just waiting for the supercomputer to be better and just focusing on physics. However, this is no longer true because of the GPU machines are almost mandatory to getting using their state-of-the-art supercomputers. So we are now considering seriously about the MPI plus X, as Julian told, and X means the GPU capability normally. And for this purpose, we decided to move to the next version of the Zeta code, and which is targeting 2026, and of course targeting GPUs. The question is that in which programming model we are interested to offer GPU capability, because language can offer and the directives can offer, but Kokkos can offer. And we decided Kokkos is the best suit for us. The Zeta code is the flagship code in France and targeting the so-called tokamak device of the modeling the ion plasma gradient turbulence in tokamaks. And basically solving the some sort of the Boltzmann equation in phase space and coupled with plasma equations. And from the numerical point of view, this equation is advection equation in the phase space, and we solve it with the semi-Lagrangian scheme for the larger time stepping. And to this scheme to be stable in numerically, we need a good accuracy of the interpolation scheme. And normally we need spline schemes. Although we know that this is not very suitable for GPUs, but in the this is the requirement from the physical point of view. And another schemes we use is the spectrum method or FEM to solve Password solver. We also use FFT here. And this code is parallelized with MPI plus OpenMP and the written in Fortran in the 50K lines. So to the next version of the Zera code, and we prototype this the Zera with the mini application, extracting the key features of the Zera, like the high dimensionality or Rosberg equation, and for the semi-Lagrangian scheme that is employed in the Zera, and targeting the exa-scale version of the Zera. And here we only decided the semi-Lagrangian scheme, or mostly decided other part, but we decided semi-Lagrangian scheme is the case, which is just used in the mini application as well. And to understand which X is suitable for us, we tried quite a lot of different X, like OpenCC target, OpenCC, and Kokkos STD parents, and SQL, or literally everything. And we also need the libraries where the Zera using BRAS and LAPACK and FFTW. And in the mini application, we tried the vendor-specific libraries for FFTs, and also for some linear algebra libraries. And as Julian told, we decided to go for Kokkos as X. The question is that, how do we offer the same capability as BRAS and LAPACK and FFTW in Kokkos? We choose the Kokkos kernels and Kokkos FFT, and for the Ginkgo for linear algebra. So this is the linear problem in spline solver we are targeting, because this part is the very heavy, the hot spot in the Zera, so we often need to optimize this part. The base case as defined, we have to solve Ax equal B because of linear algebra. Something very special is that in this case, matrix A is a single matrix, while B is a batched vectors, and in addition, the batch size is significantly larger compared to these matrix size. But the matrix size is reflecting more like the size of the one-dimensional grid. It's typically 1000. The batch size is bigger because it is the multiple of the remaining dimensions. So due to the high dimensionality of the Zera, it's quite big. So this is the multiple right-hand side problem where the batch size is significantly larger than the matrix size. And by definition, this is embarrassingly parallel in batch direction, which is suitable for GPU parallelization. There are pros and cons for the direct method and iterative method for this problem. I'll talk next. So the direct method and iterative method, we defer to the Kokkos kernels for direct method and the iterative method for Ginkgo. And there are some pros for the direct method, like the many specialized methods are available for the specialized matrix like banded or tridiagonal matrix. So we can benefit from specialized methods. And also matrix is fixed, so it means that we only need to factorize the matrix once and can be factorized on CPUs and initialization and just copy the result on GPU is totally suitable for us. And number of operations is of course fixed. Another important benefit is the memory efficiency because these operations are basically in place. The problematic part is that the algorithm is basically serial. The parallelization along batch direction only, and needed to implement multiple solvers, and actually this is the heaviest difficult part for us, because Kokkos kernels did not have this banded matrix solver support initially, so we added this by ourselves. This is demanding, of course. The iterative solver is Ginkgo. The best thing is that it works for arbitral matrix A, no matter what type, and fully parallelized with Ginkgo. So it means that the solvers already parallelized solvers are ready to use in Ginkgo. And some problematic part is that the number of iterations can be large in if condition number is big. And we cannot benefit from specific matrix structure like banded and explicitly. And the most problematic part is that it requires the extra buffers which we cannot control. And memory consumption is significantly bigger compared to the direct method. And the question to answer is how about the performance? So for the direct method, and this can be solved with the block area factorization, and so the original matrix is constructed with primes or something like this, and the major part is some sort of the specialized bandit matrix, like this one is tridiagonal matrix, and there are some parts from the boundary part, and this is typical matrix was prime. By rearranging it, and we get this type of form, which can be block factorized. And after block factorizing, we can have the two steps to solve this equation using the solver for this Q and solver for delta with other gem operations. So in the end, this Q is biggest, and this is the which can be bounded or tridiagonal. So this is the hotspot of this problem, and we try to optimize this part. And depending on the type of matrix, like tridiagonal or bounded or general bounded, and depending on degree, and we have specialized solvers in RAPAC, which is now ported to the Kokkos kernels. So in this work, and we started to implement binary matrix solvers in Kokkos kernels, and part of them are already upstream to Kokkos kernels in 2024, and already available in the GitHub Kokkos kernels. And other solvers are currently under upstreaming, under review, and they are planned to be upstream to Kokkos kernels, but currently only available on my repository. So basically, and this the type of matrix and general matrix and general bounded, or they are positive definitive symmetric bounded, or the tridiagonal matrix. There are specialized factorizers for this matrix and also for solvers, and these are all available in my fork. The Kokkos kernels implementation is quite straightforward, because then we can have this solver part, which is directly mapped to this Kokkos code, and also for the blue part is also appear here. This is another solver. It's general matrix solver, and other part is just gem operation. So our mapping algorithm to Kokkos is really straightforward and nothing strong. And also for the Q is the biggest, and this part is the subject of the optimization in this work. And we did not rely on the third-party libraries, and we using Kokkos kernel implementations only, because we can do some special optimization using that. And actually, I will tell you later, but this kind of gem can be optimized with the lambda and with the sparse operations, because on these matrices are some extent in the sparse, so we can benefit from sparse optimizations. We made a couple of optimizations. First one is the kernel fusion. The baseline is just in decoding this algorithm one in several sequential steps, different Kokkos functions, like parallel function and gem and another solver, and for the worldwide gem function. And in Kokkos, because these functions can be called from inside of the Kokkos parallel region, which means that we don't necessarily need to do separately. We can make it in one time inside a single Kokkos parallel region, like this one. And this is a typical kernel fusion for the beta, spatial, and temporal locality. And using this optimization, and we got the slight performance gain in the A100 and the minor performance gain also in the MI200, as well for Ice Lake. We measured the profile on the A100 with N-side compute, and the original kernel requires the load store of the 1.6 gigabyte, and getting this kind of the relatively high cache hit ratio of L1 and L2. With kernel fusion, we unfortunately encountered the issue for the incremented in the load and store, which means that adding these kernels inside this function, which actually bring about the extra memory loads and operations, which is not ideal. And also the cache hit ratio has decreased. So this is actually coming from this gem function, which is also demanding. As I said, this gem function can be replaced by sparse gem, which we define a very special sparse gem function by our hand, because inside Kokkos kernel function, we can do whatever we want. So we just implement by ourselves. This GemV is replaced by the sparse GemV. So this function is sparse. And actually, with this optimization, we got the significant performance gain on particularly on the MI250X. And also for this optimization, we got the initial review and for the memory load and memory store, which is really nice. And also we recover the hit ratio of the cache. In the end, we measure the performance portability of this kernel. And so this is actually the achieved ideal performance and against the achieved performance divided by the ideal performance that can be achieved by this kernel. And this is typically in the maximum, the 20% obtained for the 100 for the simplest case, and the more difficult case, and the lower achieved peak performance. And the average is the performance portability metric, where we got more like 1.4, 0.1 or something like that, and with lower for the complicated case. And the lower performance of CPU is not the main focus of this talk, but in the we have some layout issue and to get better performance on CPUs. But we can do that. And recently we got the reasonable performance on GPUs for uniform splines, which is typically used. So we are happy about this result. And in the end, we measure the performance for comparison of the direct method and iterative method by Kokkos kernels and Ginkgo. And we found that in the almost entire regime, we got the better performance of the direct method for all architectures and all regimes. And this is due to the number of iterations of Ginkgo is typically 10 to 40. And in Kokkos kernels, it's only 1, of course. And so in the end, we decided to go for the Kokkos kernel implementation because of better performance and better memory efficiency. So next, I'd like to talk a bit about the Kokkos FFT we recently developed for the Kokkos ecosystem. The motivation is that in the why we need it. And so this is because we try to use Kokkos for the photo legacy application, which relies on the FFT libraries. This may include different simulation with periodic boundaries and the plasma turbulence. Plasma turbulence is a typical demonstrator of this exa project, and it is intrinsically periodic along some directions. So we often use the FFT along this direction. Another use case may be integrating the in-situ data processing with FFTs like spectral analysis or low-pass filter. But who is not willing to get through the documentation of default standard libraries, and because all of them are different interface and depending on vendor libraries like this, and also still want to benefit from powerful effective libraries. That are the target of our users. And we decided to follow the NumPy FFT, and which may be mostly used FFT libraries, and they are still as powerful as the FFT libraries. So in the end, our APIs are for the NumPy FFT, and this is Kokkos FFT implementation. And the only difference is that the values are not returned, and also for the execution space, which specifies where this FFT is executed. Other than that, it's roughly the same. So Kokkos FFT is an open source project and GitHub and available in public, and also for their relatively nicer documentation using their Doxygen and Sphinx and Brace. And please check out if you're interested. So the key features of Kokkos FFT is that they are simple as NumPy and as fast as vendor libraries. The 1D to 3D standard and real FFTs are over 1D to 8D Kokkos views are supported, and batch plans are automatically used if the view dimension is larger than the FFT dimension. The simple interface like NumPy FFT and outplace and inplace FFTs are supported. The views are all we need and no need to access the complicated FFT APIs, and much safer APIs, and no need to use raw pointers directly. And there are many compile time or runtime errors for invalid usage. The supporting multiple CPU and GPU backends, and the FFTs are executed on the stream and queue used in the execution space. And we supporting most of the non-experimental Kokkos backend like these, including the CUDA and HIP and SQL. And FFT libraries dedicated to Kokkos backends are automatically enabled. We only support the contiguous memory layout for the moment. these are the APIs, and here basically the NumPy plus some sort of FFT prime API, and the NumPy API is just quite simple, just in here. Basically, just return value to the argument and just adding execution space, and you're done. And also for the namespaces and FFT APIs are basically equivalent to the NumPy FFT function. And also starting from the Kokkos FFT as APIs and Kokkos FFT input as implementation details, and which users should not use it. The macros are also starting from Kokkos FFT. Implementation internally, we use some sort of transpose and followed by cron creation, execution, and normalization. And also there are some functionality to allow FFT plans which is not present in NumPy, and this FFT plan can be reused and important for FFT and Rock FFT because in the plan creation is non-trivial for this backend. So plan reuse capability is quite important. The final example is that in the typical use case of this Kokkos FFT compared to NumPy, and we developed a two-dimensional and the plasma turbulence solver relying on convolution with FFT and 100 iterations. And lines of code goes shorter in Python, but in Kokkos it's roughly 2 times, and the performance gains is significant, and it's like more like 1,000 times faster on GPUs compared to the Python implementation. And even for the GPUs with OpenMP parallelization, the speed up is more like 100 times. There's animation of this one. As you can see, in the H100 is the first test, and A100 follows, and MI250X is in the follows, but it's still, you can find that in the significant speed up in the for the GPUs, and the also you can see that in the Ice Lake is still in the very initial stage, and Python is also stored. And MI250 is a linear stage, and whereas the H100 almost simulations are finished. So you can just benefit from this library and keeping the almost the same code and highly parallelized and get a better performance, although you require to write little more than the Kokkos Python version. And summary and future work. And we developed performance whatever library needed for the G0 code. And the Kokkos FFT is needed for Python solver, and the Kokkos kernel is needed for many products actually. And in this work, when we developed batch bounded matrix solvers in Kokkos kernels, where we added there and some solvers, developed some solvers and factorizers, which are planned to upstream to Kokkos kernels. And kernel fusion and source optimization lead to speedups on all backends. And the performance comparison with iterative method and direct method outperforms. So we decided to go with it. And performance degradation with general bounded dense solver and can be improved with cache blocking version, which is a little more complicated to implement. And uses of scratch memory space can accelerate our code, which remains as future task. And thank you for listening.
Thank you very much. Okay, so let's move the last talk in this seminar. So the speaker is Professor Miki from the University of Tokyo. So the title is the Unified Schemes for the Directive-based GPU Offloading. Okay, please start your talk.
Okay, so today I will talk about some interface library unifies an interface for OpenSCC and OpenMP target. And recently, actually last week, our paper is accepted and our code is now available at GitHub. So, okay, now, so GPU accelerated supercomputers are very familiar in HPC community. And currently, GPU is a dominant accelerator on recent supercomputers, as Julian showed. And the majority of GPU supercomputers are equipped with NVIDIA GPUs, especially in Japan. So current Japanese GPU supercomputers, everyone uses NVIDIA GPU. But in the world, the fastest supercomputer now is El Capitan, and the second one is Frontier. Both are AMD GPUs accelerated supercomputers. And the third one is accelerated by Intel GPU. And the fourth one is the NVIDIA GPU accelerated system. So there is some increased competition among GPU vendors. And this is some good news even for NVIDIA GPU users, because such competitions increase the performance of GPUs. And but there's also a bad news. So there's many vendors. Therefore, there's a many environment for GPU computing. So we must choose best one for the code development. Okay. Anyway, and also this is just our announcement. So we will introduce Miyabi system from next month. So please wait one more month from now. And in this Miyabi system, this is a collaboration with University of Tsukuba and University of Tokyo. And we will introduce around 1,000 GPU nodes. This is the main part of Miyabi. Miyabi Z is based on Grasshopper super chip. And also we have very small CPU only node as well. So to use this system, we must prepare code for GPUs. And there's a rough chart of GPU programming environment. And there's many choices for various users. And today, I will focus on this directive-based style for this, because this is most easier for majority of users. And there are OpenCC and OpenP target. And okay, next slide will show more details. And so we have two options for directive-based GPU offloading, but there's a pros and cons. OpenCC is the first choice for directives because this OpenCC has better function and more rich documents for users. So this is a very good point. But actually, this is virtually only for NVIDIA GPUs, owing to the acquisition of PGI by NVIDIA. So therefore, AMD and Intel will not support OpenCC. This is a bad point for OpenCC. On the other hand, OpenP target now is supported by all GPU vendors, NVIDIA, AMD, and Intel. But the function and documents are not good as OpenCC. This is a current situation. But developers must select OpenCC or OpenP target for their code development. So this is not a good situation. So we consider that the unification of the programming interface is possible or not. That is a research question. And our answer is yes, we can unify the interface by using preprocessor macros. So this code example is some example to unify the OpenCC directives and the OpenP target directives in a single code. But this implementation is very messy and terrible. So no one wants to use this style. So, and in this sharp pragma style, we cannot simplify this code anymore. But in C or C++, we have underscore pragma style directives. So by using this, we can simplify this implementation like this. Then the users can develop code like normal directives. And in this case, backend is OpenCC or OpenP target. So the functionality is much greater than the original implementation. That is the main idea of us. And so then we developed a header-only library named Solomon, and this is available at GitHub now. And so you can input the directives like this. Here is for offload. Then the linked are converted to OpenSCC or OpenMP target directives. And okay, I skipped some details, but and in this library, users can use compilers by GPU manufacturing vendors as is. So the GPU vendors will develop continuously their compilers, and users will benefit from the improvement of the vendors' compilers because we did not touch compilers. So this is just a live software library. And also, this is just an aggregate of processor macros, so users can easily edit by their own necessity. And so, yeah, so editing compiler is very hard for us, but just for macro, that is possible. Okay, here's a representative directives provided in Solomon. Basically, we have 3 types of notations. First one is intuitive notations shown in bold faces, like offload or memcopy host device or something like that. The additional ones are OpenSCC-like notation, like pragma SCC kernels group or something like that. Or also, we have OpenMP-like notation, like pragma OMP targeting group or something like that. So, and that is similar for crosses. So, for example, as independent or collapse or something like that. And in OpenSCC-like notation, that is ASE cross independent or ASE cross collapse. And in case of OpenMP-like notations, that is OMP target cross SIMD or OMP target collapse or something like that. So you can choose your preferred notation. And mixing such notation is also possible in Solomon. And the next one is, so then you can write the code using Solomon, and you want to switch the backends for your environment. And for such purpose, you should specify some compilation flag to switch the backend directives. So if you want to use OpenSCC, putting the -d offload by OpenSCC turns on OpenSCC backend, or the offload by OpenMP target turns on the OpenMP target. And yeah, and also, so this is one caution. You should also turn on the OpenSCC or OpenMP target flag for your compilers, like -acc equals GPUs or something like that. Okay, this is a very minor caution, so I guess. And there are some precautions or recommendations for uses. Indications of optional clauses. So in Solomon, we adopted comma-separated notations. Like, I show you some example code for this. Maybe here, this is a cross independent comma or secondary input or something like that. So because by this notation style, we can drop some invalid inputs if we detect it. So therefore, we adopted this comma separated notation. Also, so this is some important node for conversion from OpenCC between OpenMP target. In case of OpenCC, data directives and host directives host data directives are provided by OpenCC side, and the corresponding directive is data in OpenMP target. So conversion from OpenCC to OpenMP target is very easy. Just putting data and host data to data. But on the other hand, conversion from OpenMP target to OpenCC is not easy because there's only data, single notation. But we must choose appropriate target, data or host data. That is very difficult for just for preprocessed macros. So our recommendation is using OpenCC-like notation or some additional notation using a device or host to specify which one data or host data is better. Okay. So for now, I will show you some examples to use Solomon. And the first example is n-body simulation. In n-body simulation, we calculate the time evolution of gravitational many-body systems by solving Newton's equations motions. Okay, here's just some examples of my n-body simulations. Right? This is galaxy merger simulations. Okay, and so here's example implementation. And in case of intuitive notation, the gravity solver is like that. There's two loops. For the outer loop, we put offload for GPU offloading, and for inner loop, we put off-pragma ASE loop. But this is for not to parallelize the inner loop for OpenSSE backend, because parallelization of this loop introduces some additional atomic operations that decelerates the n-body simulations. So we do not parallelize the inner loop for gravity calculation. And also, we generate initial conditions on CPU side. That is the first line of this document. And then data should be transferred from CPU to GPU. That is done by this name copy host device. And the calculus acceleration is this one. And this is for one example. And in case of the OpenSSE-like notation, example is like this. So difference is very small, and many copy host device is now written as pragma ASE updated device. This is OpenSSE-like notation, and offload is now going to pragma ASE candidates root, and implicit process are also OpenSSE-like notation. And in case of OpenMP target like notation, but this is an example. So many copy host device is now going to pragma OMP target architecture 2, and offload is like this. And okay, this is some examples. And we measured performance of this code on various environments. First one is NVIDIA H100 on Intel host side, and second one is Grace Hopper system. This is very similar to our MIAB system, but the Grace side memory side specification for Grace side is a little bit different, but the GPU side is identical. And also we tested on AMD and Intel GPUs as well. And please keep in mind that theoretical peak performance is roughly 3 times different for NVIDIA GPUs and AMD or Intel GPUs. And also we use compilers by GPU vendors. So for NVIDIA GPUs, we use NVIDIA HPC SDK. For AMD GPUs, we use Locken system. And for Intel GPUs, we use Intel One API. Okay, as a result of measured n-body performance, the x-axis is the number of n-body particles. And for the upper panels, y-axis is basically performance, so higher is better. And from left to right, NVIDIA H100, Grasshopper, AMD GPU, and Intel GPUs. And so there are many lines, and the blue lines shows OpenSCC backend result. So these curves are only available at NVIDIA systems. And for red lines of results for OpenMP target backends. So on all GPUs, OpenMP target can run and measure performance. And so as mentioned previously, so the theoretical peak performance of NVIDIA GPUs is roughly 3 times higher than AMD or Intel GPU. But the performance difference is around twice or something like that. So AMD or Intel GPUs is also achieved good performance. And additional lines, these black lines are the dedicated to measure performance of dedicated implementations using CUDA or HIP or SQL. So this is the fastest result on each environment. And the ratio of this best performance and directive-based performance is plotted in the lower panels. The ratio is basically, here is 80% and 70% and 60%. For directive-based implementation, this ratio is also good for directive-based implementations, because the directive-based implementations is much easier for users, but we cannot fully optimize the performance for each environment. Okay, and if this is another story. So if we drop some compiler options for very sophisticated performance optimization. So in this case, we put compiler option as O first and also GPU generations. Only then the performance of NVIDIA GPU drops around half compared to the previous slide. Basically, the usage of and the best instruction for reciprocal square root is not used in this case. So please be careful of such tips for directive users. And here's another example using 3D diffusion equation. In this case, we put the OpenSCC code for Solomon implementation. So basically, therefore, we adopted OpenSCC-like notation in this example. And the measured performance is like this. And okay, basically on NVIDIA GPUs, OpenMP target with distributed directive is much lower compared to OpenSCC or OpenMP loop implementation. And in H100 and Grasshopper case, so performance is almost similar, but this is not expected because the memory bandwidth of the Grasshopper is around 4 TB per second, and the H100 case is 3 point something like that. So originally we expected that GH200 achieved much higher performance, but this is not the case because in this case the limiter is not memory bandwidth of global memory. So in this 3D diffusion equations, byte per flop ratio is 2.5, And here's the measured performance, but the converted memory bandwidth is written like this. And for example, on Grasshopper case, we obtain 4.6 terabyte per second. This is much higher than compared to the memory bandwidth of global memory. So the now performance limiter is cache side. Therefore, the difference between 800 and Grasshopper is not so huge. Also, so here is a measured bandwidth of AMD GPUs and for Intel GPUs. In this case, also, so these values are higher compared to the memory bandwidth of global memory side. So compiler achieved very good job in this case. Okay, here's a summary of my talk. So in case of directive-based GPU offloading, we have two options, and we must select one of these two options. But this is not a desirable situation. So therefore, we have developed some interface lab named Solomon, and this one is already available on GitHub. So please try if you're interested. Okay, that's all. Thank you for your attention.
Okay, so thank you again to the speaker. Okay, so that is our talk is finished, and thank you for participating in this seminar, and thank you again for our speakers to provide a great talk. And I think this is a very good opportunity to know the Kokkos and the performance portability library. And I hope that this talk will help us to decide the direction of the future development. So thank you very much for participating. Thank you. どうもありがとうございました。